Okay, good morning, everyone. My name is Liela Clarck, and today I will be presenting on my team and I's superstructure design of solvent-assisted plastics recycling processes. So a little bit of background first before I get started on what is the problem and why is it a problem. So over the next 7 to 10 years, we expect the chemical market to grow very, very rapidly due to an increase in demand, which will lead to an increase in waste, particularly in solvent waste. So as you can see from this graph here on the right side of my screen, you have the solvent waste trend in the EPA in Region 2 between the years 2008 and 2020. Keep in mind, Region 2 only covers New Jersey, New York, and Puerto Rico. So from this graph here, you can see that there is an increasing trend in solvent waste. And if you were to look at this graph on a countrywide scale, not only Region 2, the trend would also be increasing. So why is this an issue? Because this waste trend will lead to an increase in pollution, it will have adverse human health effects, and it will have negative economic effects, such as companies having to pay any fines due to improper handling of their waste, or companies having to put any capital at all into handling their waste solvents. So these are our current 3 strategies of handling waste. We have incineration, which is very costly and has a big environmental impact. Then we have on-site release, which is where you release it directly into the air, water, or an injection well. And finally, we have off-site release, which is where you simply send your waste solvent to a third-party company. These 3 are our current options, but they are not the best. One that's better is solvent recovery. So solvent recovery will improve the greenness and the sustainability of all these chemical processes. And the one reason why it is not more widely implemented is because it is a very intricate and time-consuming process. So my team and I's solution is what we did was we developed a comprehensive framework for the solvent recovery strategy that can be used across industries that will increase the ease and the efficiency of the chemical processes. So what we do is we intake a set of chemicals that are comprised of in a waste stream, and we put it into our superstructure, and we can show the optimal pathway or optimal technology sequence to recover the solvent with your desired percentage of purity. And this is going to give these companies a great foundation in their design process. So this is our framework currently. I want to focus on the left side of this figure where we have information collection, the systematized of solvent recovery, our technologies and pathways, and our roadmap. So basically what we did in the beginning was we did a lot of literature research into different technologies and their associated equations, mass energy balances, cost equations, and then we also did a lot of research into different chemicals, creating a chemical database that will include different chemical and physical properties such as density or heat of vaporizations. Once we have all of those research compiled, then we put it into designing a recovery process. So here we developed 4 stages, with stage 1 being solid removal, stage 2 being recovery, stage 3 being purification, and stage 4 being refinement. So we take our waste stream and our chemicals comprised of, and we put them in through stage 1, and it goes through all 4 stages, and out you have your recycled solvent with your desired purity or recovery percentage. In each stage, we have about 3 to 5 technologies. And another thing to note is if, for say, a waste stream does not have solids, it'll simply just bypass stage 1 and continue on to stage 2. So this is an example of one of our technology models. We have one of these per technology per stage, right? So it is a lot going into this. So here's our filtration model, where we have our feed, and then coming out will be our retentate or our permeate streams. We have on the table on the right here, we have all of our equations that are comprised of in this specific model. So we have our retention factors, concentration factors, flux balances, and our power required. Everything highlighted in red in these equations are our parameters, and everything in black are the equations or the variables. So we have one of these models per technology. We take all of those technology models, so there's 10 technologies total, and we put it into this superstructure approach, where, again, there's 3 to 5 technologies per stage, times 4 stages. And what we do is we input our waste stream, and it will go through each of the 4 stages, including the bypass streams, and it'll give you out your optimal technology pathway. But what it will do is it will compare every single technology sequence. and it will compare them based on a cost analysis and an environmental impact assessment. And all of our technology models are programmed via GAMS, which is the General Algebraic Modeling System. And the solution algorithm that we use is MINLP, or the Mixed Integer Nonlinear Programming. So now that we have our superstructure, we have an example case study where we designed to recover ethyl benzoate from a Johnson-Matthey chemical process. This chemical process can be illustrated in the figure on the left, where what they did was they took a PET packaging waste and they put it through a dye removal where they swell it using ethyl benzoate, and they further filtered that ethyl benzoate back out, and that's where we come in. We have the solvent recovery of the dye separation. And then the PET is then diluted, it's filtered out again using ethyl benzoate, and you have your solvent PET separation, and finally you get your 96% recycled PET. So down on the table on the right are what we put into our superstructure. So we have our list of chemicals, our mass flow rates, our inlet mass fractions, and finally we have our output requirements. This will go into every single case study that we do. And these are the results that you obtain. So the optimal pathway that our strategy selected was for stage 1, sedimentation, stage 2, adsorption, stage 3, microfiltration, and it ended up bypassing stage 4 due to the fact that after stage 3, the desired output of ethyl benzoate was obtained, so there's no need to spend any money further refining it. On the left side of this figure, we have the beginning of our cost analysis, where we have the dollar per year for technology per stage. So for example, sedimentation in stage 1 will cost approximately $932 per year, and following down through all 4 stages. Further results that we have are, we break down our cost analysis depending on the type of cost that it is. So we have annualized capital costs, we have our raw materials. So for example, labor costs contributes 10.74% to the overall cost. So the overall cost of this optimal technology pathway is approximately $394,000 per year. And when you compare that to, say, the most common incineration costs approximately $7.72 million per year. Now to look at our environmental impact assessment, we have incineration that has a lot of degrees of magnitude greater impact than solvent recovery. So instead of incinerating this waste stream that would release a lot of CO2 into the environment, solvent recovery has a lot less of that environmental impact. So in summary, what we did was we established a superstructure framework approach to find the optimal technology sequence for the recovery of different waste solvents across industries. And we optimized the recovery of ethyl benzoate in the Johnson-Matthey process. And for future work that we want to do, we want to cultivate more case studies working collaboratively with industry partners. And we also want to develop and publish a software tool that will increase the efficiency of our superstructure. And then we want to get and incorporate industry feedback to further increase the efficiency and the accuracy of our overall strategy. This is my research team. And so with acknowledgements, I would like to thank the American Institute of Chemical Engineers for letting me speak today, the US EPA, the Rowan University Chemical Engineering Department. My team's link can be found at the bottom here if you want to see any of our more work. And my name is Liela Clarck. My contact information can be found on this slide, and thank you for listening today. Yes.
So when you're including the parameters in the superstructure, for example, how many characteristics of your solvent or your waste stream do you need to consider to make it reliable?
So we have a bunch of different chemical and physical properties that are required. I would say approximately 5 to 7 minimum that we need in order to give you a result per chemical.
This number 5 to 7 based on, thank you. This number 5 to 7 comes from what sort of analysis?
The different variables that are required according to the equations per technology.
So
for the presentation, and I'm interested in your particular role in this project as opposed to the team. Did you do the simulations yourself, or what was your role in that?
So I helped with some of the research, literature research. I also helped mainly with the coding of the GAMS programs where we model all of our technologies to make sure that they run efficiently and that they're accurate, and then producing the results and then the appropriate figures. So kind of a little bit in each part.
Thank you.
Hi, thank you for the talk. So in this technology pathway, it's based on the waste stream that comes in, and you figure out which particular solvent from the waste stream you want to recover. And then I guess my question is, what if there's more than one? Would you run it just multiple times, or can it handle like mixtures of multiple solvents you want to?
Yes, so we can handle mixtures. We have in our, it's not just one outlet stream. We also are trying to currently implement where we can have different mixers between stages so that if you have a solvent that you want or have a certain chemical that you want from stage one, we can separate that out and continue to recover your second desired chemical.
Okay, cool. Yeah, that was kind of a next question.
Yeah.
Thank you. All right.
Thank you.
Good.
In your cost analysis, you showed that this process that you have is way cheaper than incineration.
Yes.
And I'm wondering why, because incineration seems to be like a simple, I understand it generates CO2, but why is it more expensive compared to this multi-step process?
So basically, according to whatever cost equations are with the technologies that are selected, because like I said, it takes every technology sequence possible out of all 10, and it compares them across a cost analysis and develops the least expensive one. And then we run a separate model that will run how this specific waste stream would give the results for incineration, if I'm wording that correctly, and overall based on the cost analysis and different chemicals in this waste stream ended up being cheaper, if that answers your question.
Okay, I guess it goes to where the data on cost come from, right? That's
Yes.
what you put into the model.
Right.
And do you know where it comes from? Where those assessments of cost per kilogram or per whatever come from? Where did you input the data in the model? What's the source?
So there's multiple sources depending on the technology.
Sure.
Again, that would be more of like our literature research background, our citations that we have, but the cost equations are from credited journals
Okay.
that we use.
All right, thank you.